type of addition reaction is the formation of halohydrin. This type of reaction is very similar to the one that we just saw in the previous video, in the sense that it goes through the same bromonium or chloronium ion in the middle. So let's talk about it. In a halohydrin formation, we go from a double bond, and then what we will add across that double bond will be a Cl and an OH. Okay? And the way that this happens is very similar to the halogenation reaction that we just saw. The first step is the formation of that three-member ring. Remember that that three-member ring will form from both the top and the bottom, so it will give us two three-member rings, and that will be the slow step. That's exactly the same for both type of reactions. But what is different in the formation of the halohydrin is that because you have water in the mixture, what will happen is that instead of these X minus that left in the reaction coming back and attacking, what will come back and attack is the water. So we have that halonium ion, that three-member ring with a positive charge on the halogen, and it will be opened up by the water that will attack. So the water will come, attack, opening the three-member ring, and that's how we end up with a halogen and the water on the other side. And the last step is the deprotonation of the water, so we end up with the alcohol and a neutral species. Let's talk about the stereochemistry of the halohydrin formation. So again, because we go through that three-member ring, so in this case it will be, we will form this and the other one that is both of them up. Remember that Br has a positive charge in both cases. Now, when the water comes in attack, the water will come from the opposite side because of steric hindrance, right? So here we have the lone pair. It will come from the bottom, and in the other case, it will come from the top. So in the right side case, in here, the water will be a dash, so it will be this one right here. And in this one right here, because the water comes from the top, the water will end up as a wedge. And so these two are trans enantiomers because they are up, down, down, up. In the case of halohydrins, the stereochemistry is quite particular because for unsymmetrical alkenes, the preferred product has the electrophile bonded to the less substituted carbon, which is here, this one, the Br, that's the less substituted carbon, and the water ends up in the more substituted carbon. I'll talk about it more in the chapter where I talk about epoxide openings, and I will come back to this situation. But the reason is because when you form this one right here, when you form that intermediate right here, the water is going to come and attack from this side right here. Right? And the reason for that is because that will give us a more stable intermediate. Don't worry about this now, but this is just for you to know. But I'll come back to it when I talk about epoxide openings, and I'll bring back the halohydrin formation when we have unsymmetrical alkenes. Halohydrins have been used in synthesis in so many different reactions. So here we have one example in which OH and Cl are added across a double bond, and then there's the formation of an epoxide, because remember that Cl is a great leaving group, and then that will eventually lead to estrone. So in here, this is the step that we are talking about in this chapter. And here we have a summary of halohydrin formation. So remember that the mechanism is 3 steps, that the rate determining step is the first one in where the halonium ion is formed, that no rearrangement can occur because we're not going through a carbocation. When it comes to regioselectivity, the electrophile will end up to the bonded to the less substituted carbon. We'll talk about it more in another video where I talk about epoxide opening. And for stereochemistry, remember that this is an anti-addition. Remember that when you have that three-member ring with the Br, right? If I have here my alkene, right, the Br is here, my nucleophile will come and attack from the opposite side. So in this case, if my Br is pointing towards me, the nucleophile has to come from the opposite. So the Br will stay up, but now the nucleophile will be down because it attacked from the opposite side, right? So this is what we call an anti-addition, because both elements that we added across the double bond are on opposite sides.